after Northwestern, or do you have any plans at all, or you can go first, I guess.
I'm still a freshman, so that's
Yeah,
a little
it's
bit
all
off.
right.
But right now, I'm planning on at least grad school. We'll see
To start.
what happens in college.
Right.
I don't know, you might like yourself too much right now.
I'm planning on grad school for astronomy.
They offer an astronomy class here, right?
Yep.
Yeah. Fun. All right, well, let's get started. As she said, Dr. Aric Waltz, I'm an optometrist here in town. I'm a graduate from Northwestern, so I think it's really cool to have the opportunity to come back and speak to you guys. And as you guessed, we're going to be talking about optics today, pertaining to optometry. We're going to try to keep it as basic as possible. You guys know optics can get really complicated once you get like the formulas and all that. But I'll try to keep it as practical and as simple as possible. Optics is the foundation of pretty much everything optometrists do in our everyday practice and work. But I do like this picture because the left picture is the picture of the microscope slit lamp. We don't just like flip dials 1 or 2, checking your vision, how well you're seeing. We also treat and manage ocular diseases, which I think is the most fun part. It kind of takes away from the monotonous kind of daily routine of what we actually do. But we just do a little bit of everything. Optometry or optics is super important in optometry. Like I said, it's the foundation of what we do. We have 3 rounds of boards that we have to take. The first round of boards that we take is pretty much everything we've ever learned in like our entire life. And optics counts as 40% of that test. And so a huge portion of what we need to know. But yeah, let's go ahead and get started. And super cool that you guys have this class actually, because we didn't when I was here. A little bit about myself. I already said I'm a Northwestern grad, but I went to Spirit Lake High School. I went to the University of Missouri St. Louis College of Optometry, graduated in 2020. Pretty cool year to graduate as an optometrist in 2020. But work experience, worked at Clarkson Eye Care in St. Louis for a year before my family moved back here. Right now, I work at Family Eye Care here in Orange City, also in Hayward 1 day a week. And I'm also at Promise Community Health Center. And so today we're going to talk about just a bunch of different types of optics. I'm going to try to highlight what I think is the most important stuff or the most foundational pieces. We'll start with geometrical optics. And she said you guys kind of just covered that in your course. Talking about light properties pretty quickly. Refraction is a huge one. Reflection, interference, polarization, divergence, all that fun stuff. Prisms, lenses, glasses, contacts, differences between the two. And obviously you have mirrors, colors, all of the instruments, telescopes, microscopes. We're not going to get into too much in depth on that stuff, but I just mentioned that's just part of geometrical optics. And then geometrical optics, when you're in optometry school, it's a 4-year program. Geometrical optics, you take the entire first year that you're there. The entire second year, you're taking ophthalmic optics, which is more optometry, practical, hands-on things. Talking about lens characteristics, materials, plastics, metals, hypoallergenic materials, index of refraction of lenses, impact resistance, ABI value, which is the quality of a lens, weight, UV protection, and then you get into the frames, materials, components, and then I think the fun part is the adjustments. Say someone brings in a pair of glasses, or too tight, too loose, you have a temple that's completely bent the wrong way. They just teach you how to adjust things. And you do a lot of it when you're in clinic and on the fly. I think that's the best way to learn. And then obviously contact lenses, a little different than glasses. Optics is pretty much the same. You're dealing with a thin lens system as opposed to a double-sided lens system. And the difference between contacts and glasses, the prescription-wise is vertexing. We'll get to that here later. But contacts have a lot of benefits. I always try to push contacts on people that wear glasses, not just because, it's like a money thing. I don't really care about that, but you do have a lot of benefits in terms of your field of vision. You're not looking through a frame. You have all that extra view. They move with the eye, less prismatic effects, especially for higher prescriptions. Definitely good for activities, sports, that kind of stuff. They're more convenient. So the first thing we'll talk about is refraction. So as you know, refraction is the bending of light as it passes through one medium to another. And that picture up there on the top, when we're checking someone's glasses prescription, we're doing what's called a refraction, because someone's coming in with blurry vision. And what we're trying to do, we're trying to bend that light so it focuses on the retina, and that's what makes it clear. So we're saying 1 or 2, flipping those dials, are basically just changing where light is focusing, trying to make it clear. And this is kind of like our bread and butter as optometrists. Ophthalmologists, the surgeons can do this. You can teach people to do it, but we spend like 2, 3, 4 years learning how to do this. It's actually an art. I mean, yeah, you are flipping the dials and you're telling us kind of what you think is better, but there's a lot of psychology that goes into it, a lot of practice, and so really important. But anyways, yeah, the Snell's law is the equation that you use for refraction. And so N1 sine 1 equals N2 sine 2. And so let's get into some examples, but refraction in the eye, the eye is basically a system of refractive surfaces. And so if you're looking at the eye, you have really 6 different systems here. And so we talk about where light is being refracted at in the eye. You have the front surface of the cornea, the back surface of the cornea, and then the lens. And so the front and back of the cortex and the front and back of the nucleus. And so it can get pretty complicated when you're dealing with like 6 different surfaces that light's being refracted at. But how light is refracted in your eye really determines what your vision disorder or how you're seeing. And so if I draw this here, so let's draw a bunch of eyeballs. So let's just say this is a normal eye. And so when light is coming into the eye, it's going to be refracted at the cornea and the lens, and it's going to focus right there on the retina. The retina is that back yellow surface of the eye. It's like the film of the camera. You want light to focus on that spot so that your vision is clear. You know, it sends a signal to the brain. But normal vision, light is going to be focused right on the retina. On the retina, that spot's called the macula. And so when you see older people get macular degeneration, basically it's just that spot that light is focusing on. Your central vision is deteriorating, which is why it can affect your vision so much. But anyways, let's go on to the next one, which is myopia. Myopia is nearsightedness. And so that's basically saying the eye is too long or the cornea is too strong. And so that light, when it comes in, it's going to focus in front of the retina, making your vision blurry far away. And that's why when you're nearsightedness, things are clear like right here, but things are blurry far away. And we're going to go to hyperopia, which is farsightedness. This one, just the opposite of nearsightedness. The eye is going to be too short, or the cornea is not going to be strong enough. And so that light is going to focus behind the retina, causing blurry vision. And then astigmatism. So astigmatism gets pretty complicated. So I'm just going to basically show you this picture and we'll kind of move on from that. Astigmatism is when the cornea is shaped a little bit differently than normal. So usually your cornea, that front surface of your eye, is going to be spherical, like a basketball. But with astigmatism, that cornea, you get a little bit of abnormal curvature to it. And so it basically causes the light to split up a little bit. So let's say, let's give you one line here. Let's say one beam of light focuses here and the other focuses here. So that's astigmatism. You have 2 different focal points for that. So those are kind of the main vision disorders there. So just an example of Snell's law. And so I have pretty much the problems worked out here so that you guys can go back to it and see how it's worked out. But pretty simple here. If a beam of light is passing through air and comes into contact with a piece of glass at an angle of incidence of 20 degrees, what is the angle of refraction? So in optometry school, you're going to see a lot of these types of questions. Pretty simple. You just got to know the equation, put it in the equation, solve for a variable. You guys are sure really good at that. But the equation, Snell's law, again, n1 sine 1 is n2 sine 2. And so the ones, you're always going from where you started to where you're going. So n1, the refractive index of air, which is 1. And then you have the angle of incidence, just 20 degrees. N2, refractive index of glass is 1.44. And then we're solving for what that angle of refraction is. And so you can kind of plug the numbers in. So yeah, 0.342 equals 1.44 sine 2, divided by 1.44. So 0.342 divided by 1.44 equals sine 2. You take the inverse sine of that and get 13.7. And so the angle of refraction is going to be 13.7. And so I like doing these types of equations because they're pretty simple. You just solve for the variable. And then when you get into the eye, it's going to be the same thing. I just use different anatomy. So if light is passing through the aqueous humor, which is the anterior chamber here, and the light is passing into the lens at an angle of incidence of 10 degrees, an angle of refraction of 8.91. What is the refractive index of the lens? And so you're going to use the same equation, plug in the variables and solve, and you're going to get the refractive index of the lens is 1.48. And so, like I said, pretty simple. You can make many different examples yourself if you want. Just put different numbers wherever to practice. And so Snell's law, I think, is a really important equation in optics. And then reflection. Reflection is basically, I think, one of the most simple equations of optics. It's the angle of incidence is the angle of reflection. And so basically light is changing directions when it comes into contact with another surface. And obviously you're dealing with mirrors with reflection. In the eye, I don't really have a mathematical example for this because it's pretty simple. But reflection in the eye, what that optometrist there is doing is called the Hirschberg test. And so we use this test a lot for kids who you have a hard time getting them to say anything, they're not cooperating. You can do a lot with just shining a light in someone's eye to be able to tell a lot of information about them. And what he's doing is shining that light in someone's eyes. We know that most of the light is refracted into the eye. Some is absorbed, but also you get some light that's reflected as well. And so when you're standing directly in front of someone, if you're shining that perpendicular to their eye, that light's going to be reflected right back to you. So you can see a little bit of a light reflex there. And so it helps you determine their ocular alignment. Pretty much if someone's got a lazy eye, called a strabismus. If someone's got perfect normal alignment, that reflex is going to be in the direct center of their pupil. If someone's got an inward eye turn, that's going to have a light that is towards the outside of their pupil, and the other one's going to be normal. Same thing as you go on down the list. If someone's got an outward eye turn, that light reflex is going to be towards the nose. If someone's got a lazy eye that's going upwards, that light reflex is going to be to the bottom. Vice versa for someone's eye if it's kind of lazy eye pointed down. And then that kind of leads me into prism pretty well. Prism is all about dispersion. Light, it spreads light into its individual wavelengths. And how does it do this? It's because prisms are a double refractive surface. As we know, the visible range of wavelengths of light is actually pretty small. It's like 400 to 800 nanometers, I believe. So when light is passing through a prism, different wavelengths are bent differently. Shorter wavelengths like purple, blue, they bend a lot more than the longer wavelengths like red. And so you can see how it just allows you to see those individual colors. Prism is important in optometry. We deal a lot with it. And basically what you can do is you can put prism in glasses. And when we're talking about prism in optometry, we're really not talking about, we're really not talking about colors and spreading those wavelengths. We're talking about how it affects your visual system. And so we use prism to correct double vision and misaligned eyes. And so if you can see this picture down here, let's just imagine that there's an eye right here and it's pointed straight ahead. This eye is maybe deviated a little bit out. And so as the object is right there, if this eye is looking out, he's not really looking at that object. And so that normal eye is going to see an object right there. This eye is going to see an object over there. So that causes double vision. And so what we have to do as optometrists is make it so you're not going to see double, because, you know, issues driving, headaches, all that kind of stuff. And so what you do is you put a prism in front of the eye, and you can do that by putting in the glasses, as I said. Prisms move light towards the base, which moves the image towards the apex. And so it kind of shows you how it moves that image towards the apex. And pretty much it's going to be putting that image where that eye is looking. And so, yeah, you use it to correct double vision. When you correct that double vision, it can allow that eye to come in alignment with the other. So you're not going to have as much of a lazy eye anymore. That's pretty big. So you use it for that. That will cause this eye to kind of straighten out a little bit. Use it a lot for kids as well. Kids do get a lot of lazy eyes. And it's really important that you correct a lazy eye in kids, because if you don't, if they have a lazy eye, as they're developing, their brain will be like, oh, I have a really good eye size, straight size work, and I'm just going to forget that other eye. So that eye, the vision just starts to get worse and worse over time. And so you reach a critical age, which is around 12, to where there's just no going back. And that vision is just going to be bad the rest of your life. And so if a kid's young enough, you usually do surgery to correct like a amblyopic or strabismic eye. But a lot of times you can use prism as well, basically just allowing the eye to learn, develop, and so both eyes get better. Actually, it's pretty cool. So if you see it in clinic and you prescribe a prism, sometimes their vision can be pretty bad, like 20/40. And if they're young enough and they actually wear their glasses, their vision can actually get back to 20/20 over time, as long as you're within that critical period before age 12. After that, like I said, it's kind of just shot. But so you use it for that as well. You use it in vision therapy a lot. So vision therapy, if someone say, when you read, you converge your eyes. And so you converge your eyes to read. If someone has issues doing that, they can have a lot of eye strain. They can get headaches. And so you can actually prescribe a small amount of prism in the glasses just to help your eyes converge a little bit. And that helps with that as well. You can create eye exercises with prisms by changing them. It's like an eye workout. Pretty cool, actually. So prisms are pretty fun. I actually brought some prisms too, you guys can take a look at. So as you see, you kind of got a base and an apex. So you can even see if you close an eye, just put it in front of your eye. You can see how it moves that image. So pass those around, just take a look at them. So now we're going to get into lenses, and lenses that deal with glasses and contacts. Glasses and contacts, it's all about the divergence of light, convergence, divergence, where light is focusing. And I think it says in the name, the most fundamental equation in optics for optometry is called the fundamental paraxial equation. And I know it's just a bunch of letters, but the top one, F equals L prime minus L. F is power measured in diopters. Capital L is vergence. In the bottom one, we know that N equals refractive index. The lowercase l deals with object and image space. And R is radius of curvature. And I'll give you guys all examples so you know how to kind of plug those in the equations there. And so, let's see. Plus lenses, as you can see, they converge light. So a parallel light is hitting that lens. It's going to converge it together. And they're lenses for hyperopes. And so if we go back to this picture, when lenses converge light, we know that light is behind the retina. So what we want to do is you want to move it back to the retina. So by doing so, you put a plus lens in, which just converges that light a little bit more than your eye normally could to make your vision clear. Other one, a minus lens. If parallel light is coming into a system here and hits a minus lens, it's going to diverge that light, which is exactly what you need for nearsightedness. And so let's put a minus lens in here. When parallel light comes through, it's going to just kind of diverge that light a little bit more. So instead of focusing in front of the retina, it's going to focus on the retina. So that's kind of, just the optics and physics behind what glasses actually do. It's all about focusing divergence of light. And we'll go through this example of lens power. And so the power equation, how to find a power. So this is how to find the power of a pair of glasses, basically just depending on where your clear point is. And so if you're nearsighted, and your clear point of vision is 50 centimeters in front of your eye. So if you're wearing glasses, take them off. Like my vision, a little blurry, it's clear right here. If that's 50 centimeters in front of the eye, you can use that equation, F equals 1 over F, which is just that focal point. And so the power of the lens is 1 over negative 0.5 because in meters. And so the power of the lens is going to be a -2 diopter lens. And so this person is a -2 diopter myope, they're nearsighted. Example of a plus lens. And so we're going to deal with a system here. So for this question, if an object is 35 centimeters in front of a plus lens of power +8 diopters, where is the image located? And so we're going to assume that object space is n equals 1 and image space n prime equals 1.5. And so again, I'm just going to plug and chug, put those numbers in the equation. So we're solving for, let's see, we're solving for where that image is going to be located at. So power of the lens, we have +8, n prime, we have 1.5. We're solving for L prime, which is where the image is at again. And then you're going to subtract 1, which is n, and then divide that over -0.35, which is where the object is located. And so when you go through that, solve it all out, the image is going to be located plus 0.29 meters. And so that is going to be behind the lens. Minus is always in front of the lens, plus is always behind. We call that image space. And so that's kind of just a little introduction to see, if you have a certain power of a lens, if an image is here, or if an object is here, where is the image going to be? We deal with a lot of that in optometry school. Sometimes you get into multiple lens systems, and so it can get pretty complicated there. Same thing for a minus lens. You're going to be doing that exact same thing. This time you just change the variables up a little bit. And so if an object is 50 centimeters in front of a minus lens of power -12 diopters, where is the image going to be located at? And so you're going to be putting those variables in the equation, solve it through, and you guys can do that later on your own. I don't have to bore you with that this time, but when you actually get to the end, the image is going to be located 0.09 meters in front of the lens. And so when you look at that, I told you minus is kind of the object space here. So if the object is in front of the lens, like why is the image in front of the lens too? So that's kind of when you get to what minus lenses actually do. Minus lenses, like we talked about, if you have parallel light coming through, it's going to diverge those rays. And so we call it ray tracing. So if the light diverges, you're never going to see where that image is going to be at, because it's going to diverge for like infinity. And so you got to trace those rays, and the image appears, even though the image is not there, we call it a virtual image, the image appears to be right here in front of the lens and stuff. Pretty cool stuff there. And then the last thing we'll talk about is how to write a glasses prescription. And a lot of patients will ask me to give them their glasses prescription or what it is. And it's kind of hard just to like tell them what a glasses prescription is, because like I said, there's a lot of numbers in it. There's a lot of optics, anatomy behind it. So I can tell someone, oh, your prescription's a -5, and I mean, they don't really know what that means. And so a myope, like I said, nearsightedness, you're going to have a minus prescription. Minus, let's just say the right eye OD is minus 4.5. The left eye is a minus 5. The SPH means sphere, so that means that they're just nearsighted. There's no astigmatism to it. Hyperope is going to be the same thing. This time, though, you're going to have pluses in front, meaning they're farsighted. Astigmatism, always a little more difficult, always a little bit more to it. You're going to have 3 numbers here. So the first number is going to tell you if you're farsighted or nearsighted. And so this has a minus number, so they're nearsighted. Second number is the amount of cylinder, we call it, which is the astigmatism part. And so that number is pretty much the magnitude of the difference between those 2 focal points there. So obviously, the higher the number, the more astigmatism you have, the further those 2 points are from each other. Last number is the axis. The axis of astigmatism is usually 1 to 180. And so when you have astigmatism, the glasses and the power need to be oriented a certain direction. If you have it off by even a little bit, it's going to blur your vision. So that's just the last number is just the orientation of where that cylinder power is. And then the last one, a presbyope, we'll just assume that they're nearsighted. Presbyope is when you kind of get to your 40s, 40, 45, and that reading gets a little more difficult. I'm sure all your parents have come through that already. The lens inside of your eye, it becomes less elastic, and so the lens doesn't change shape as well. And so you have a more difficult time focusing and reading. And so that add power on the bottom just does that reading for you pretty much. And so you see that either like in a bifocal and contacts, you have multifocal contacts too. And just basically adds power to the system, allowing it to focus more light on the retina. And so there is a difference between your glasses and contact lens prescriptions. It all deals with the distance from the eye. Glasses, we know they sit about 10, 15 millimeters in front of your eye, whereas a contact lens sits directly on your eye. And so that changes what we call the effective power of a lens. And so that's why I don't think it's a good idea. We always talk about a bad idea of buying contacts online, is because A, they don't really require a prescription from an eye doctor. And so we could just give you your glasses prescription and you put the same thing in the computer and they send it to you. It's not going to be the same prescription. A lot of times they can exchange their own brands, but if your prescription is off by even a little bit, it causes focusing issues. You can get headaches, migraines, and it's just not good for the eyes. And so the way you calculate it is, it only really matters if the power of your glasses is greater than 4 diopters. And so let's say a glasses, if it's -3 for each eye, the contact lenses are going to be the same, -3 for each eye. However, in this example, in the glasses, that right eye OD, you're going to go from -6.25 to a -575. Left eye from a -7 to a -650. And there is an equation for this too. It's actually a pretty long equation. And so you can actually solve these out and work out the problems. We also have calculators, or if you do it long enough, you can just take a look at a number and you can tell what their prescription might be. So minus is always going to be less minus in a contact lens. A plus lens is always going to be more plus in a contact lens. And then astigmatism, a little different here. You're going to vertex that front number if it's greater than -4. The second number, like we said, is the astigmatism. It only comes in 0.75, 1.25, 175, 2.25, and so on. So you got to round that number down. So it's going to go from a 2 to a 175, 1 to a 0.75. And then the axis, you're just going to round that to the nearest 10. And so that'll give you a good idea what their contact prescription should be. Different instruments, and so I'm not going to go into too much detail about this, but you can when you take a look, you can tell how complicated these systems really get. You have a microscope there on the far left, and then you have a telescope. Let's see. Yeah, telescope there. You got lasers, and then just a simple camera up top. I always use the camera as an analogy for the eye. You have a kind of a lens here that you can widen and close the aperture. It's basically how you focus things, and then the film can be like the retina on the eye. Systems there. And then, yeah, a couple pictures of my kids and all that stuff. We always do that when we're in optometry school. We always have, and the lecture with pictures of our family. So, yeah, I tried to keep it as simple as possible, a little bit practical. I know it probably wasn't the most entertaining thing in the world, but it is super important in everything that I do. So, yeah, you guys have any questions or anything?
Yeah, so I have 2 questions.
Yep.
So for these, like when you're talking about like correcting like a lazy eye or whatever, for these prisms, do you actually like put these in like a frame lens and then wear them and then correct the eye? Or like how does that like work with like?
Yeah, so to determine the magnitude of a lazy eye, you do what's called a cover test. And so you'll move like an occluder from one eye to the other. And if you do that, so if you just do it on one eye, like move it from one eye off, you can see the other eye like move from side to side. Some people it's bad enough where you can see their eyes like way off in a different direction. But to do that, let me see real quick. To determine the magnitude, what you do is pretty much on their lazy eye, you would just put the prism in front of their eye and keep on covering this eye. And you would change the prism until you see no more movement in that one eye. And so it's kind of how you determine the magnitude of it. And then you can trial frame it, just kind of put it in a pair of glasses and see, can you see single? Is it clear? Are you able to fuse the image? And then if everything is going good, then you're able to make that into a pair of glasses pretty much. And so, yeah, it can be kind of fun.
And then like what's the one that in the case had like a red, it was just red.
Oh,
what's that like for?
This one. So you can deal with red lights to determine the alignment of the eye too. So there's a bunch of different tests to determine the alignment. You have, I don't know if I have it. You have a occluder called a Maddox rod. It's like a red circle with a bunch of lines in it. You can actually use this in there too. But pretty much when you look through it and shine a light at you, you're going to have like a line that forms. And then you just put a chart in front of their eye and like, is that line on 0 or is it to the left or right? And that tells you where their eye is kind of looking at. So yeah, you do it with a lot of colors too. So kind of another way to do it. I don't really ever use that test, but it's there. There's different ways to do it.
How do the prisms interact with like the lens like corrections?
Yeah.
Would that, like if they have a prism, would that mess with the prescription? Or
Not necessarily, no, but it can do the opposite. So if you have a really high prescription, it can actually induce prism in the eyes. And so if we, I told you how, I'll put it down here so you can see on the Zoom. If you have a prism, we talked about how there's a base and an apex there. I draw an eye, just kind of like the eye. If you put a really high minus, so I'll put a minus one in here. Actually. So there is a minus lens. If you think about it in terms of half, it's basically like putting this type of lens in the system there. It's kind of like a minus lens. And so a lot of times when you're reading, actually looking through the lens, you're kind of looking slightly nasal. And so that's if this is the right eye. And so a lot of times you could be looking through like this part of the lens, and that kind of induces prism, a base in prism, we call this, because the prism, the nose is here. That means that you're looking at a base in prism, and it kind of moves the image this way. If you have a really high prescription, a high minus, when you're looking through that part of the lens, it kind of makes your eyes diverge a lot. And if you're not good at diverging your eyes, you're going to need probably extra prism in your eyes to cancel that out. And so, yeah, prism doesn't necessarily change the glasses prescription, but the glasses prescription can cause prism in the lens. I don't know if that explanation made sense, but it's kind of difficult to talk about, but Yeah, there's there's prism in every pair of glasses. Any prescription has a prism in it because of, like I just talked about there. But it only really matters if your prescription is super high, is when you have that prism used in it. So, yeah, any other questions?
Do blue light glasses actually work?
Yeah, I haven't like tried it myself, but the science behind it, I do believe it. Pretty much what that blue light is doing is it's just filtering out those shorter wavelengths of light. And those wavelengths are just shown to cause strain on your eyes and fatigue on your eyes. And so by filtering that out, you're just getting rid of that extra eye strain and fatigue. You know, different people have different opinions on it. You know, there's lots of studies, lots of research out there. So I believe, because I'm going to believe research that's out there. So yeah, it definitely works. During COVID, I had a lot of patients, a lot of kids that were doing homeschooling on computers like all day long. And there was a lot of kids that were just complaining of eye strain and fatigue. And a lot of those blue light glasses did help.
You're telling me like because like I had to get blue lights because like I just get like headaches in my eyes and just. So you're telling me it's not a placebo effect, it actually works.
Yeah, I mean, there could be a lot of different things wrong. Yeah, it could be the blue light. It could be a lot of screen work. Do you wear glasses or contacts or anything?
No.
It could be that you have like a little bit of a glasses prescription that you don't know about, to where, you know, when you're not wearing glasses and you're reading, it just makes it more strenuous. Could be that your ability to focus or accommodate isn't as great. And that's kind of when you get into reading glasses and stuff like that. But the first line of something to do is usually just blue light glasses, and see if it helps or not. If not, if you get a lot of eye strain, a lot of headaches in reading, I would just try like a really low reading glass, like a +1, those ones that you find like at the pharmacy in the store. Those they'll help you out too. So it's the next thing to try.
On the, when you were showing like the example of prescriptions,
Yeah.
why was it like why are they OD and OS?
Yeah. So OD is like, that's like right eye and left eye. So OD means right eye, oculus dexter, left eye, OS, oculus sinister. I think it's like Latin or something. Latin maybe? Yeah. Yeah. So yeah. So kind of nice to know. You know, before I went to optometry school, we didn't have optics here. I shadowed Dr. Hickman a little bit, but I didn't really get into the details. And so I didn't really know anything when I went to school. Like, what the heck is like OD, OS, like, but yeah, that's basically all it means. It's just right eye, left eye. So it's good to know when you get a glasses prescription too. That's what it means. So I think it might spell it out for you on the actual prescription that we give you, but yeah. Yep.
They all have 20/20s, they're jerks.
Lucky. I was the same way until I went to optometry school, and then you study a lot, and then your vision becomes more nearsighted. Just because when you study so much, your life becomes like right here, and so your eyes actually adapt to that distance. And so I studied so much that my eyes just got used to like this distance, that we look far away, it's like now that's blurry and this is clear. And so I just have like, I kind of like -1, so I'm a little bit nearsighted now after all that studying. So if you plan on doing a lot of studying, you may notice that if you feel like your vision is getting worse far away. So it happens. It happens. So even if you have a really big difference between the two eyes, say like one eye is like a -7, one eye is like a -3, you know, with the glasses, yeah, a big prismatic effect, and that can also affect like the image on your retina. So plus lenses, we know, are like they make things bigger, they magnify things like a magnifying glass. A minus lens makes things smaller. And so if one eye is like a lot stronger than the other, the image that goes to the retina can be a lot different size. That can cause issues too. It also, the weight of the lens is just off. That's when I think contacts are a good idea too, because contacts, you don't have to deal with lenses. You don't deal with prismatic effect of where you're looking because they move with your eyes. So yeah, I think that's a big benefit of contact lenses as well. So
Do you have to deal with like eye dominance at all?
yeah.
Any sort of like calculation?
Yeah, that was actually really cool because when I was in high school, I did not, like when we did like archery classes, that kind of stuff. It's like, man, I suck. I cannot hit like the center of this bullseye. It's because I learned that you got to learn your dominant eye. I'm right-handed, so usually when you shoot an arrow, you're going to use your right eye. I'm right-handed but left eye dominant. And so a cool thing to do actually is you can use like one of these circles here. All you do is kind of put your arms out in front of you and make like a little bit, make a triangle so that you can see that circle. With both eyes open, yep, you're gonna make it so you can see that circle. Close your right eye. Can you still see it there? Close your left eye. Is it still there? No, so that basically means that you're left eye dominant. So you can, yeah.
That makes sense. I remember like doing
What
that.
circle?
Just use like this one here.
Yeah.
Okay.
So put your arms out in front of you so that you can see. Do you see the circle
Yeah.
in there? Okay, keep looking at it. Cover your left eye. Can you see it still? Cover your right eye.
No.
Okay, so your right eye dominant. Yep.
Okay.
So that's a good, quick way to do it.
Is there like a scientific like meaning eye dominance?
Basically, your dominant eye is always going to be the eye. It's not necessarily clear because both eyes see pretty much the same, but it just kind of has like an advantage, I guess I would say. And so we deal a lot with dominant eyes when you're doing like multifocal contact lenses. If someone is dealing with like a reading prescription, sometimes I'll add some extra magnification to their non-dominant eye, so that way they can read better, but it doesn't affect their distance vision because their dominant eye is unchanged. So you deal with a lot of this in optometry. You know, baseball, you probably deal with that a lot. Now, I'm not sure if you're like right-handed, if your left eye is dominant, maybe that's better. I don't really know how that would work. Like football, if you're a quarterback, if you're right-handed and left eye dominant, it's probably a little better because that's your downfield eye, and you can probably see a little better there. Yeah, there are always implications to that.
I remember doing like that test when I was doing hunter safety.
Yeah.
When I was a little kid.
Wish I'd remembered that. That would explain everything, like shooting a bow and arrow. But yeah. There's a lot more that goes with it. Like I said, we'd also do a lot of treatment management of disease, glaucoma, macular degeneration. Around here, I get a lot of like metal, or I get a bunch of like farm stuff, whatever they're dealing with in their eyes. And that's always fun, I think. That adds a little excitement to the day. Not for them, but for me. Because yeah, with the metal, it's pretty cool. You got a little device, you got to kind of get the metal off the eye. If metal is on the eye for even like an hour or two, it causes rust to form on the cornea. And so if you get the metal off, there's like rust on the eye. So you got to drill that rust off with the drill. And it's pretty fun. But
So they always stress like eye protection.
yes.
Like, because I work bridge construction, and like anytime we're like cutting or like drilling, like we always have to have those.
Yeah. If you get something in the eye, not fun. The cornea has a lot of nerves to it. And so anything on the eye, even like the tiniest of scratch that I couldn't even see with the microscope, can be super painful. And so anything on the cornea just honestly really sucks. But the good thing is the cornea, the epithelium heals like really quickly in like a day or two. So it goes away pretty quick, but yeah.
Worst thing is definitely concrete in my eye.
Yeah, that's not good.
So I forgot to put my glasses on, and then like when because we had it like coming like through like the pump truck, and it splashed right in my eye. I'm like, oh guys, I just like took some water, got it out, my glasses on.
Yeah, a little too late.
Yeah.
The thing about concrete too is you don't just see a little concrete, you see a lot of concrete because it splatters in the eye. It's not just like a piece, like you gotta, and then it gets hard and you gotta scrape all the pieces off. And
I do with concrete here.
yeah, it's not fun. Always to wear safety. Help.
So this is not something you talked about, but it's like the reason why like a laser would be dangerous for the eyes because it would damage the retina.
Yeah, so lasers of certain wavelengths, basically it just kind of burns the retina. And so if you're looking, like if you look at the sun, like when they had the solar eclipse, I don't know how many years ago, I think I was the first year on optometry school. You know, if you didn't wear your glasses and looked at that, you did a lot. Is that you? You were one of those?
No, I just remember like there was a lot of people that were just like cool, and I'm
Yeah.
like, no,
You probably should do that. But pretty much, yeah, what that's going to do is you're looking directly at the sun. It's called solar retinopathy. When that light hits your macula, it's going to burn that spot and cause basically you're going to see when you look inside of the eye, it's basically just a dark spot. You're burning that macula and you're pretty much just killing that part of the retina. And so say you're 20/20 before, maybe you're 20/40 after 20/50. Nothing's going to change that. No glasses like in front of your eyes is going to make you see any better. And so I think I've heard of a couple people. Gosh, when I was in the clinic at school, we had a bunch of people come like that, a couple days, a week or two after. Like, I look directly at the sun. Like, can you look at my eyes? I'm like, all right.
I don't know if we can do anything.
Yeah, I'll take a look and see. But yeah, so yeah, that's why you don't want to look at the sun. Not good.
So what is LASIK?
Yeah.
Yeah, so LASIK. Let me erase all this. This is an eraser, right?
Yeah,
I'm not just letting. Okay.
no, an eraser.
So I wonder if it actually
These are got headphones for.
He
might
did.
actually.
PT eraser.
It's okay if I like go on
Yeah,
there.
go for it.
So it's actually easier if I just
Just hit exit.
escape. Okay. Let's go with plus. So let's show some pictures here. So pretty much with LASIK,
I've got it on extended display, so you'll have to move it over to the other one.
drag it over. Drag it over to.
Just drag it to the right.
Yeah.
Right side. Oh, man. Oh. Now we're there. Okay, so. The picture didn't turn out to be very big. Okay, whatever. Anyways, so, like I said, the cornea is that front surface of your eye, pretty big refractive surface of light. And so what they do is they're basically changing your vision so you don't have to wear glasses by changing the shape and the power of your cornea. And so what they do, they're not going to do anything to the epithelium because the epithelium just regrows back and it changes. And so what they're going to do is they're going to cut a little bit of a flap on the cornea. They're going to push that back. They're going to laser the cornea. And so usually, if you're nearsighted, they're pretty much trying to make that cornea flat. And so they're going to laser the center of the cornea so that's flatter. They're going to put that flat back on. Boom, check mark. Vision is corrected. So that's kind of how LASIK works.
So this is one time you want to have a laser.
Yes, that is an example of a laser. Yeah, yep. But it's not like a laser in terms of like anything with vision or how it's like bending light. This is more of like, I wouldn't say like a damaging laser or a laser that's like a cutting laser, I guess. I don't really deal much with those types of lasers, but yeah, you're just kind of flattening and shaving off that cornea. Sometimes, you know, if you're nearsighted and your cornea is too thin, you can't do LASIK because you only take so much off and you only go through the cornea. So they take a lot of measurements there. This is an actual image. Where's my mouse? Oh, there we go. Bear with me. Okay, so this is like an actual eye. This is what it'll be like. You know, they're gonna have a speculum holding the eye open. They're gonna have a laser or whatever. Flip that flap over. Boom, boom. I've just had done a bunch of these surgeries. Sometimes it's like 10 seconds. Just like it is zap, 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 zap. You're basically looking at a light directly above you. Don't want to move your eye, obviously. When I'm done, they just flap it over, put a couple eye drops in. You don't need any stitches or anything. That there's a pressure in the eye, and it's like sticky enough, I guess, where it just stays in place.
So they don't do like that. Like, does it hurt? If you just like put the top of.
They numb the eye. Yeah, they're gonna numb you. Yeah, that would hurt a lot. Like I said, there's a lot of nerves in the cornea, so. Like a tiny little scratch would do a lot of damage, just like a big scratch.
So the
Epithelium,
yeah. It's adjusted to a certain shape of the cornea. So when you first like flip it back over, when did it like sink in?
No, because there's more layers to the cornea. You have like the stroma, which is the middle part of the endothelium, and so that's kind of what they're changing the shape of, is the middle part called the stroma. When you put that flat back on, it just kind of conforms to the shape. It's kind of like putting a contact lens on your eye. Yeah, contact lens could be like more convex. When you put it on the eye, it's gonna like basically take the shape of your eye. So that's kind of what this is doing. It's kind of acting like you're putting contact back on the eye. But basically, you're just putting part of your eye back on your eye. So, yeah. Your question, you guys? Oh.
Well, shall we thank Dr. Waltz?
Yeah.
Fantastic.
Right, prisons aren't just used to make rainbows.
Right. That was the big takeaway.
Big takeaway. Use them for lazy eye. So if you see someone walking around the street